All right, so this is why the graph is getting curvy. Now, based on that curvy graph, if that shows it getting faster, think about what your velocity versus time graph should look like. So I'll pop you back over to your prediction there. What should that velocity versus time graph look like? Oh, come on, man. So we know position versus time graph. So on the, like you have the two sets of graphs, right, on the paper. So the left side is for your prediction, and then the right side is for what we actually see. So over here you predict, and over here you record what actually gets displayed by the motion detector, okay? So if it's that, because it's getting faster, what are we saying? Let's look at the thing. Boop. All right, now we're pretty universal on the velocity versus time graph expectation, what we're expecting that to look like. So let's check it out through the magic of graphical analysis. What, bro? So, hey, what's up with the Rock of Gibraltar here? What's going on? What's this? That's when it hits the thing. I don't want that part. I want when it's doing its thing. So 1.75 kind of looks like that, okay? There's a little bit of a hump at the beginning. That's because I started too close to the detector. I'll try to fix that. But notice that for most of the time, which is to say about a second here, that's pretty linear. That's pretty constant in terms of the slope on that graph. So velocity versus time graph, I would implore you to draw something. Oh my goats. Something that looks like that, okay? So if that's what that looks like, what's our acceleration versus time graph going to look like? Well, everybody and their mom is pretty confident that that's a horizontal line in the positive part of the graph, at least the people drawing it, okay? Oops, I'm not going to just draw that. Let's look at it. Acceleration versus time. Wow, what is this huge snaggletooth here? What's this fang? That's when it stops. So again, I'm going to change the time here to be 1.75. And for the majority of this motion, it's a flat horizontal line. Let's see if I can even find the value of it. That looks like a bed, Mr. Harding. No, it's a flat horizontal line, kids. It's got a value just shy of 1, right? So 1 meter per second squared. That's the acceleration. All right. This thing says to draw a motion map to include both the velocity and change in velocity arrows, okay? So what would the motion map look like? Thinking back to the lab from the last couple of days. Your motion map's going to look just like what that we already did? La cinta, see? Yeah, right? Just like those tapes over there. So my initial marks are going to be rather close together, but then over time, they're going to spread out because it's getting faster. So my velocity arrows are going to start out short, but then they're going to get longer. So there's a new twist that we're going to add into these things. Oops, and actually I should have an initial dot that is just a dot, because I start with a velocity of 0. So here's this new thing we're going to add in. I'm making hollow dots, and I'm putting these arrows on there. What the heck are these arrows? Okay, so here's where I need you to lose your neighbor there for a second, okay? Because this is something new, and I want to make sure you understand what I'm doing. So these little hollow dot arrows, basically what I'm saying is this little hollow dot arrow is what am I going to add to my velocity arrow to get my new velocity arrow, okay? That's kind of maybe hard to get your head around, but basically it's like if I take this velocity arrow, the hollow dot arrow, if I add it to it, that's how I get the next velocity arrow. See how that works? And then if I come over here, whoa, that's not the right thing to move. If I grab this velocity arrow, adding this hollow dot arrow to it, that's how I get that next velocity, okay? So if I take this velocity to get the next velocity, I just add that to the end of it, boom. The hollow dot arrows represent the change in velocity. So like in this case, based on the acceleration graph, I know I'm adding 1 meter per second to the velocity every second. Well, this thing's not moving a second, but maybe it's adding 1/10 of a meter per second every 1/10 of a second. So that's what those represent. All right, so while people are catching up on that, I'm going to go ahead and set this up for the next thing. Number 2, let's see, now I got to change the ramp. Detector is still here on the left side. And again, this defines where 0 is. You can't see it because there's bushes. But here's the detector. The card is going to start out by the detector. I'm going to give it a push up the ramp. Come on, man. Stay put. There we go. I'm going to give it a push up the ramp. Push. And then I'm going to pounce on it at the highest point. Okay? So what's that going to look like if you draw it? If I give this thing a push and then a pounce. Okay? Push and a pounce. The detector is right down here at the bottom. So once you've drawn in your motion map, this is the second one. Yeah, push and pounce. Think about it on paper, and then once you've thought about the second one on paper, go ahead and think about it on the internet.
Where did you do it again?
You bet. Push, pounce. Detector's down here at the bottom of the ramp. So think about when is it fast, when is it slow. Think about this. Paradox up here. Think about this too. When is it fast? When is it slow? If the motion detector is 0, what is its final position? Not 0. And the sheet is telling you, right? This is. Oh, I guess I need the other one up, don't I? Right, this is 0, this is positive there. I'm going to give it a push. Ooh, let me fix that. Give it a push, and then I'm going to stop it at the highest point. Push and a pounce. Don't worry about the motion map right now. I just want you to be thinking about the graphs here. Hey, are you kids catching this? I'm not letting it come back down. I'm giving it a push, pounce. It's going to end here. So what does that tell you as far as the final position? Wow. Oh, look at you people thinking.
Yeah.
I hate males.
Hate females.
I hate males.
See, why you have to add
What? All right. So here are some of the different things that I'm seeing in there right now. We seem to be in agreement on the acceleration graph, which is weird because that's the new thing. How do you already know how to do the new thing? But then all these velocity time graphs have some commonalities, but where should it start? Which half of the graph should it be in? Position versus time graph, where should it start? What should be true in general of the shape of it? Is it getting faster, getting slower as it goes? I didn't put yours up there, sorry.
Wow.
Well, reflect on it and think about some of the patterns here.
Could maybe better if I just grabbed it.
Why do you look?
Yeah, me too. Actually, it does too.
I would think those
He stops it at
so I never go back down. And it stays.
So it's like this. Try to forward.
All right, let me throw this at you. I think we have all four different types of parabolas here, right? Yeah. Okay. So, which of these four have the starting position correct? This is the detector. This defines where 0 is. Here's the cart right by it at the beginning. Here's the cart at the end. What should be true of the position relative to that? So think about which two of the four have that part correct. It becomes interesting after I push it. Okay, we're not considering what's happening before I pushed it. So after it leaves my hand, what's true of its speed relative to any other point in the motion? Okay, so which of the two have that part correct? Okay, so talk to your neighbor about it here a little bit, my gosh.
Right going side. Which or the bottom? I don't think it's. I don't think it's maybe the top right.
Aye.
Position.
Yes, sir.
What is this for? I think it's just.
There's just
All right. So let me give you this. So here's ABCD, and for ABCD, which ones show the cart starting out fast and getting slower, right? Can we agree that's what we're seeing here? After it leaves my hand, it's moving fast, but then it's slowing down and it stops at the highest point. So which of these show, and there could be more than one, which of these show the cart getting slower, right? Starting out fast, getting slower. Additionally, here's the important thing. Why? What is that in the position time graph that shows you that it's getting slower? What feature of the graph shows you it's getting slower? So I'm not just curious as to which ones, but what is it about those two? Find the pattern there. Keep going, Austin. Tomas, is there any other graph that has that same pattern to it? I like your thinking, Ava. All right. So in the spirit of moving things along, let's check in with some of our friends here. We've got A covers a lot of position in a short amount of time and then changes less position in more time. A, because it starts out with a steep slope and then slows down with less steep slope at the end. A, the slope is steep in a positive direction at first. Oh, man, people are changing what they're saying. All right. Anyways, we go over and take a look at A. If we split this in half in terms of time, so here's the end of it. This is me trying to estimate half. Look at how much position, look at how much the position changes in the first part of this motion compared to how little the position changes in the last part of that motion. Okay? So there's a lot of position change in the first part of the motion, not much at the end. Or just in general, the slope at the beginning is very steep. The slope at the end is very flat. Okay? Which other graph has that same understanding in the slope? I didn't get a lot of you to answer with two graphs here. I just got one. Do you see another graph that has that same pattern showing a thing that gets faster? Ooh, we can do it this way. It starts out faster, and then ends up slower. Hit up the Pear Deck, bro. I really need you engaging your brain in this today because we're going to identify really important patterns that you're going to make use of throughout the rest of this unit. Then we're going to go away for 5 days and forget all of it and come back. Right? Wednesday, Thursday, Friday, Saturday, Sunday. Weekends kind of don't count, but
I thought yesterday was Friday.
Today is Friday in a way.
Yeah, but I really thought yesterday was Friday.
That's tough. All right. How'd we do? We seem to be in pretty good agreement that, hey, D also has that pattern of starting out steep and ending up flat. D's not the right choice here though because C is not the right choice here because it starts at a position away from 0 and ends up closer to 0. That's not what's happening here. But it does have the starts out fast, ending up slow thing. Okay? So different degrees of rightness to this. Let's check it out. So I'm going to switch this back to position. I'm going to switch this back to 5 seconds. And I'm going to swing this. Push and a pounce and a push. How do we do in our prediction? We get the shape? Yeah. All right, so around 2. Boop. And I don't think we go more than like 1.2 meters. Let me get just a little bit more of this. 2.2. There we go. Right? That looks kind of like what A had predicted. So there's the position time graph shape. Now, if that's the position time graph shape, what should the velocity versus time graph look like? I need you guys to put some more thought into that at the moment. What should the velocity versus time graph look like if this is the position graph and velocity is the slope on the position versus time graph? I got 10 people not even in on the pair deck right now. Come on, man. Get your graph in there. What should the velocity versus time graph look like if this is the position time graph? We now know what the position versus time graph looks like. Wow. That's some stuff. All right, let me give you a few examples of what I'm seeing. Okay. So those have some things in common, but they differ in other ways. So have a discussion on that with your neighbor and see if you can come to a consensus on what this should look like here. And let's say this too. Some of you are like graphing beyond what you need. This is only interesting after it leaves my push to just prior to my pounce. Okay? So don't worry about after I've pounced or before I've pushed. We just want to look at the motion where it's accelerating. All right, I'm going to take it to these two. So think about where they're agreeing, but where they're differing. All right, so I need you in the pair deck. Not worrying about math class. I need you to worry about this pair deck. And are you an A or a B person? And why is that the way to go? Again, you're weirding me out because you both agree on the acceleration graph. But then is it A's velocity graph or B's velocity graph? All right, so let's lock this down quick just so people aren't changing stuff. All right, so we got it's B because it's not a negative slope. It's just a slope that goes from more to less steep but does not even have a negative slope. B because the velocity doesn't go negative. We stopped it before it could go negative. A because it starts slowing down in the negative direction. B because the velocity starts in the positive and moves towards zero when it slows down. A because the slope of the velocity should be negative and constant since it's slowing down. Plus it starts at rest or zero. A, the velocity is zero when you start, okay? So consider those statements and have a conversation with your neighbor right there. Sort them out. And if you don't know one fun fact about your neighbor here in a second, I'm going to batter you. Introduce yourself. Talk to your neighbor. Come on, Kiana and Abdul. Can't be the two quietest kids in class sitting right in front of me. Kiana, this is Abdul. He speaks 3 languages. Abdul, this is Kiana. She's the Jenny Finch of softball. No.
Jenny Finch is a pitcher.
What's that?
Jenny Finch is a pitcher.
Are you not a pitcher?
She could be.
Aren't you? What are you? Are you a slapper? Oh, okay. A shortstop.
Slash, she could do anything.
She's the Megan Rapinoe of softball.
Who's that?
Bro.
That's what I was going to say.
All right. Let's see who is more convincing. Go back over to your velocity versus time graph. Sort yourselves out. Shouldn't we be on Thursday's schedule today? Doesn't it kind of feel that way?
Yeah, I was thinking that Tuesday.
I'm going to just be worthless by 6 hours. We have AFT today?
I don't know.
Oh, man. I'm going to get kicked out of the library during AFT, I bet.
Really?
Because it's AFT, bro. My teacher's just a joke.
That's what I do. I go to the library.
I'm kidding.
Imagine being here for 8. I know. That's kind of funny.
Take it easy, girls that are here for 2 classes a day.
Exactly.
3. Okay,
Yeah.
so
Why was I
3.
looking at your schedule yesterday?
Probably. Wait, mine or?
Yeah.
Ours are like the same. Basically.
Yeah.
Except, yeah.
You're here like 2 periods.
3. And well, 2 like classes and then pals.
Yeah.
So. Because we're not even here for pals. Yeah.
We don't go to West High.
But we have Kirkwood.
There you go.
That's
the thing.
Does it count for what school?
Ouch.
Yeah, but like, is it like the stickers?
It's both.
Does it go to I?
It's both.
All right, so here's what it looks like right now. Mad props to who is that? Mad props to Roberto there for the Argyle. We still have some folks that are expecting that and some folks that are expecting that. So let me throw you a little something to maybe settle that argument. Look at the position time graph that we made. We already have this. We know this is correct. What is true of the slope here at the very end? Okay? So if I were to kind of extend that out, what's true of the slope at the end? Compare that to what's true of the slope at the very beginning. Okay? And then see if you can make sense of why our velocity versus time graph looks like that. There's 2 parts here. What's going on here? What is this? This is the pooch. This is the pooch. This is the cart going up the ramp. So, come on, friend. So I'm drawing that for the velocity versus time graph. And then seemed like we had a pretty good understanding that the acceleration graph is going to look like the hell.
So I was right.
What's this fang here at the beginning? That's the push. Here's the acceleration when it's going up the ramp. Kind of wavy. You don't want the push. We just want the part where it's showing constant negative acceleration. Why is there constant negative acceleration? Because the slope on the velocity graph is constant negative. All right, so there's your graphs. So your last act as a physicist in the month of November is to think about situation 3. Situation 3, the detector's at the bottom of the ramp. The cart is going to start out, yo, don't pack up, bruh. Okay, hey, detector, that's defining where 0 meters is. Cart's starting up here. I'm going to let go of it. It becomes interesting once I let go of it. And then, whoo, I'm going to pounce on it right before it hits the detector. Okay? So, think about the shapes of those graphs between when I release it and when I safely pounce upon it there at the bottom. Cat-like reflexes. That's why they call me the Puma. No. Who? I have to go early to learn how to run the new credit card system. For popcorn. Yeah.
The middle graph, why doesn't it start at 0?
I've been really sad when I no longer have to break somebody's
I wasn't listening when you started talking about that.
So, yeah, varsity tip off.
Is it because like
Come see your girl.
it says it's the slope of the position versus time, and it's like going like up like fast, and then it like stops.
Oh,
So it like stops so fast.
okay.
Trying to
I guess that makes
multi-sport
sense.
thing, that's what
I get it. And then he adds like 7 more things onto it, and I'm like, what are you doing? Okay, do you want your real opinion for something?
Were there any clear girls
Yeah.
in the girls' committee? Or did they not swim for girls? That's the boys.
Yeah, right.
Who's our boys swim team representative here? Nobody? Owen? Swimming? Not going for the Harding trifecta?
Yeah, we remember Dr. Quinn. Well, the other one.
Someone's really
Full Harding. I think they swim with like Williamsburg, I think the boys swim with like that's what they do, right? Do we still have, do we have any girls from Washington? There were some girls that drove up from Washington. Yeah, 35 minutes every day to practice.
Hey, Kate, do you think we should do that activity with Vega?
Weird.
Should I tell Grandma? Should I tell you what you're feeling? Yeah. No, you can't tell him your issue. I want you to help me.
I will. In December. You've been pretty right so far today. Austin, you show it. No, because you show it starting out by the detector. I'm getting farther away. It's going to start out away from the detector. And closer to it. So its final position will be close to 0. Bro, lab. Yeah, did you get a friend to stay with you and help? Oh, man. Kenzie, do you have a 3rd hour class?
What?
Do you have a 3rd hour class?
Yeah.
Let's
go.
Okay, fair enough.
Sorry.
Right. Sorry. Cool. Matt's just going to collect some more data.
Okay.
Uh,
Should I do the same? Good luck, Rachel. Good luck.
yeah, we're steeping it. We're not going to like look at it as a class again. It might be of interest. Did you guys have 3?
We took 3 different files.
Did you change the book LW?
No, we just took 3 trials.
Yeah.
I don't know what color.
Alright. Yeah, grab stuff. And then, are you a music person at all? Oh, boo. If you get a metronome app, the metronome will tell you when to mark every 2 seconds. Every 3 seconds. Alright, snack.
I think I'm gonna have this one few books.
Yeah, that seems fair.
Traveling to Fort Diggity Dodge. In action. Who's gonna be there? Which cousin? Right? Exactly.
Oh, hey, what's up, Mark? Oh my God.
And she goes,
Right.
and I go,
Oh yeah. Okay.
and it drops like, and we go,
Yes.
and he goes, Mom, your flashlight is still on. And so then I'm gonna waste more. I literally thought I was getting murdered by my 8-year-old, and she had really long hair. She gets out of bed. She's like, Mom. Never touch that. He will yell at you from his head. And stare. Yeah. And she sleepwalks. But
Creepy. Creepy. Uh-oh, that's not gonna work. Are those the posts that you use
I think so.
on the day? That might be part of the problem too. What are these guys?
I thought these looked short.
Oh yeah. Let's check wide Wi-Fi issues.
Do you know what I would put into the metronome for 1 every 3 seconds?
20 beats per minute,
Okay.
right? That'd be right. Oops.
Okay, so.
With it, I should ever remember to shut off the screen.